Okay, in this problem I've got helium going through an insulated nozzle at steady state. Okay, temperature at the inlet is that, velocity is that, 150, temperature, pressure are given. I know the area at the exit. I want to find the mass flow rate. Okay, so first of all, we recognize at steady state the mass flow rate is constant through the entire nozzle. Okay, so the mass flow rate in and the mass flow rate out are the same. Now, that mass flow rate again is going to be AV over V, where this is the area that's given to me. Okay, the velocity, okay, is really what I'm trying to find, if I can find that velocity. And then this V is going to be, well, that V is, I get that from PV equals RT, right? Because this is an ideal gas of helium, right? I know the pressure and the temperature, I can find R. So basically that mass flow rate is AV over, again, V, which is going to be RT divided by P. Okay? So really what I'm looking for here is that final velocity. Once I get that final velocity, I should be able to find the mass flow without any problem. Now, for a nozzle, okay, the equation, the first law equation is H1 minus H2 plus V12 minus V2, because on a nozzle, the kinetic energy change is significant. So it's basically a change in enthalpy equals the change in kinetic energy. Everything else goes to zero. It's insulated, so Q goes to zero. There's no work being done. There's no change in potential energy here. Okay. Now, because this is helium, I don't have any charts to look up H1 and H2. Okay. So to find H1 and H2, okay, you'll remember that I use Cp times T1 minus T2. Plus, again, this will be the same, V1 squared minus V2 squared all over 2. Okay, where Cp, you'll remember, is 2.5 R for a noble gas. Okay, because helium has constant, it's a monatomic gas, it has a constant specific heat, and that specific heat is given as 2.5 times R. Okay, and you can look that up in well, it just should be known for those monatomic gases. That's what Cp is. And I use that Cp to find delta H. Okay, so I know T1 and T2, so now I can find delta H. I know V1 is 150 feet per second, so all I'm really looking for now is V2. Okay, so solving for V2, okay, I get the square root of 2Cp times T1 minus T2 plus V1 squared. Again, it's just taking that equation and rearranging it, solving for V2. Once I get V2, that's what goes up into this equation to find my mass flow rate. Okay, so going through this and saying, okay, so 2 times Cp, which is 2.5 times R, where R, in this case, I'm going to use the 1545, because that is the foot-pounds per pound mole, but then I need to divide that by the molecular weight for helium. And for those keeping track at home, the molecular weight of helium is about 4. I'll go ahead and look that up though. Helium, 4.003. Okay, times the change in temperature, which is going to be inlet is 550, exit is 400. Okay, let's go through some units on here, right? So that R, this guy right here, the units on all of that is going to be, again, that'll be foot-pounds per pound mass. That'll be actually that's pounds force per pound mass degrees Rankine, right? And it's pound mass because I did the molecular weight here. Okay, this is in degrees Rankine, so I have foot-pounds per pound on this guy here. Okay, what I need to do is I need to get this into, and this is degrees Rankine. What I need to do is I need to get foot-pounds per pound into feet squared per second squared. Okay. So what I do is I take this times the gravity term, okay, to convert. So let me just write that. So it's 32.2, and this would be pound mass feet per second squared all over 1 pound force, right? So the pound force, that kills that pound force. This pound mass kills that pound mass. Degrees Rankine kills that degrees Rankine. And look, I've got feet squared per second squared, which is what I'm looking for. So once I have that all in feet squared per second squared, I can go ahead and add 150 squared, right? Because that's the initial velocity. So this whole thing, when I plug that into my calculator, again, this is R, right? And then I just need to do this conversion to go from, again, foot-pounds per pound mass to feet squared per second squared. And it's that relationship between what a pound force is related to a pound mass. Okay. Anyway, my velocity coming out is then 3056 feet per second. Okay, so again, much higher than this, which is the point of the nozzle. You've got this incredibly large change in velocity that we're looking for. Once I have that, I can take this, pop it in up here where my area is 0.0085. My velocity is 3056. R on this is, again, I'm going to use the 1545 divided by 4.003 times the temperature. And again, this is the temperature at the exit, which is 400, divided by the pressure, which is 40 psi, which I need to take times 144 to get in pounds per square foot to get in line with the foot-pounds up here. Plugging all of that garbage in, I get a mass flow rate of 0.97 pound mass per second. Okay. So again, the main thing here is recognizing, again, how mass relates to area and velocity and volume, knowing that volume can be found because it's an ideal gas. Then using my first law equation, where I have specific heat for my monatomic gas, to calculate that final velocity. Once I get that final velocity, plug it in. Now, of course, in English units, there's lots of messy conversion factors, and hopefully you follow those. But the general, this first law, okay, and then the fact that it's a monatomic gas, constant specific heat, helps me, solve that velocity, conversion factors, all that good stuff, and we're good to go.